Okay, so moving on, the second part of the orthogonality property. We need to show that if k is equal to j, so that means if we have in that integral the same function multiplied to itself, then that integral will be not equal to 0. And hopefully we can actually find it. Once again, let's remember where this j naught comes from. In other words, let's remember that j naught stands for the root of the Bessel equation of order 0. Okay, so if you plug in j naught of x into the Bessel equation of order 0, obviously you end up with 0. And let's also remember the two differentiation properties which we used before. This proof will use a little bit of a more trickier sleight of hand, so to speak, but hopefully you can follow it through. It's nothing really but integration and some calculus 1 little tricks, really calculus 1 tricks if you think about it, which are not obvious if you think in retrospect. I mean, it's not like something you would be expect to have an inspiration on the spot, but with a lot of trial and error, so to speak, one can actually show this. And I should mention that there are various proofs of the same thing. This is basically a version that I choose, which I think it's maybe slightly easier to follow through. One particular step I want you to keep in mind, because you will do that also often in the case of actual problems involving these Bessel functions. So the first thing I wanted you to do, that step, basically is to somehow rewrite this in terms of j naught of x. So we're going to start by making a change of variable here. Simply because, in fact, it might be easier to use these rules if you have just x instead of alpha x inside of the Bessel function. Because remember, if you have alpha x instead of x, you have to pay attention to that chain rule when you use these differentiation properties. And that might be tedious. And so that's why it might be preferable to do that, the following substitution. So denote by a new variable, let's say z, denote alpha jx. So just a use substitution, basically. And that means dz is equal to alpha j dx. And the integration bounds, if x is 0, then obviously z is 0. If x is equal to c, then z is equal to alpha jc. So with this change of variables, my integral, the integral from 0 to c x j naught alpha jx j naught alpha jx dx is equal to the integral from 0 to c alpha j, and instead of x, you're going to write z over alpha j, j naught of z, j naught of z, and then instead of dx, is going to be dz over alpha j. So you can leave the integral in terms of z, but in order to actually follow through with these rules, let's go back to x. So remember, z is the dummy variable, right? I mean, you can rename it x or any other letter if you want to at this point. Okay, so the same integral is now from 0 to c alpha j, 1 over alpha j squared x j naught squared of x dx. So it boils down basically to trying to compute this integral of x times j naught squared of x. And this is where the sleight of hand comes a little bit, which is not that obvious. Let's keep this in mind. So again, I need to somehow figure out how to get this integral and show that it's not equal to 0. Let's go all the way back to the Bessel equation. Okay, so again, if I plug in j naught of x, I should end up with this. And I want you to notice that, first of all, the first two terms can be combined into a product rule, just the calculus 1 product rule. So I can basically go back to this equation here and write the first two terms as the product between x times j naught prime of x prime. Okay, so if you apply the product rule here, you get x j naught double prime, and then it's going to be x prime times j naught prime, which is going to be the middle term. So this is basically the product rule that will give you these two together. And then copy the second term, and this is equal to 0. Furthermore, now let's multiply both sides of the equation by x j naught prime of x. We're going to force a power rule in this case. So let's multiply that, and we're going to end up with x j naught prime of x prime times x j naught prime of x. And in the middle, we have x squared. I mean, not in the middle, the second term, we have x squared j naught of x, j naught prime of x equals 0. So when you have a function multiplied by its derivative, you can come up, or you can think of it as coming from the derivative of square of that function. So, j prime is like the derivative of j squared. This times the prime of that is like it's like the derivative of this raised to the power 2. So to be more precise, these two together can be combined into 1/2 the derivative of x j naught prime of x squared. All right, so how would you do the power? Well, again, let's practice with some calculus 1 now. So you're going to have 2 times whatever is inside, and that's why I put the 1/2 here to cancel it out. And then times the derivative of the inside. So 2 times whatever is here, that'll give you this parenthesis, and follow with the chain rule times the derivative of the inside. Maybe it's easier to see it here on the second term. Leave the x squared out, and you can think of j naught times j naught prime as the 1/2 the derivative of j naught squared of x, right, which is 2 j naught prime of x. All right, so at this point, one can get rid of the 1/2 because there's 0 on the right-hand side. And follow through the computation. I know it might not be obvious where that leads to, but hold your horses for a moment. Let's do now the integral from 0 to c alpha j all the way through. I'm going to obtain in the end this integral by doing these steps, essentially. That's the goal, to eventually end up with what I have here. So integrate both sides from 0 to c alpha j. And now pay attention here in the first part, it's the integral of a derivative. So here I can apply the fundamental theorem of calculus right away. So the integral of this part is just x j naught prime of x to the power 2 evaluated between 0 and c alpha j. And here is going to be the integral from 0 to c alpha j x squared, and then the derivative of j naught squared of x dx, which again we know this is equal to 0. All right, at this point, we're going to use some of this property that we have here before. J naught prime is minus J1. All right, so let's replace J naught prime with minus J1 and then evaluate everything at C alpha J. So this is C alpha J to the power 2, right, because it's raised to the power 2. J naught prime is minus J1, but raised to the power 2 is just J1 squared. So that's going to be J1 squared evaluated at C alpha J. And on the second integral, let's do the integration by parts first. So outside the integral, we have x squared j naught squared of x evaluated at 0 c alpha j minus the integral from 0 to c alpha j. Move the derivative from this to x squared. X squared prime is 2x, j naught squared of x dx equals 0. So I hope at this point, again, if you go all the way back to what we tried to compute, I hope now should be obvious where that leads to. We're going to continue in a short while, but just ponder for a moment what we want to obtain. In the end, we want to obtain that this is not equal to 0, or to actually compute it and show it's not equal to 0. And notice that by doing these manipulations on the Bessel equations, we ended up with that integral, which we will be able to compute from that equality. Let's clean up this a little bit. So this is c squared alpha j squared j1 squared of c alpha j. Here we're going to plug in c alpha j again. And then 0 for x. And here, let's move the 2 outside of the integral. And move on from here. All right. Remember, never forget where alpha j come from. Alpha j is nothing but the root of j naught of alpha c equals 0. So remember, this is equal to 0 because alpha j is simply the root of that equation. This is not equal to 0, by the way. So remember, the roots of Bessel functions don't overlap between functions of different orders. So c alpha j, or alpha j, is the root of this for the j naught of c alpha equals 0, but those roots will not make 0 for other Bessel functions of different order. This is of order 1, right? So this is basically you leave this as it is, essentially, right? I mean, because this is not going to be equal to 0. Just this one is. So from this, obviously, we can find the integral that we wanted to find in the first place, right? So the integral from 0 to c alpha j, if you move it to one side of the equality, equals c squared alpha j squared j1 squared of c alpha j. And then just divide by 2, and we're nearly done. Okay, so the integral from 0 to c alpha j, we're going to write it nicely on the second page. X j naught squared of x equals c squared alpha j squared j1 of c alpha j divided by 2. Okay, so let's actually do this on the same part on the next piece of paper. So we don't break the continuity of the argument too much. So again, we started from the integral from 0 to c x j naught of alpha x j naught of alpha x dx. And we show that this is going to be 1 over alpha j squared, the integral from 0 to c alpha j x j naught squared. And we just proved on the previous page that the integral from 0, this integral here, is actually c squared alpha j squared j1 of c alpha j divided by 2. And alpha j squared cancels. These are non-zero roots. So this is equal to c squared j1 c alpha j over 2. So we finished the orthogonality property. In other words, we show that when we take the integral of the product of the two Bessel functions at alpha jx and at alpha kx, we get 0 if j is not equal to k, and we end up with c squared j1 of c alpha j over 2 if alpha j is equal to k. This is analogous to what you showed for the sine function. The integral of sine of nx, sine of mx was 0 if n is not equal to m, and it was pi over 2, if you remember, was c over 2 in the interval 0c if n equals m. This is the complete analogy, except that you need a weight function. And another difference, of course, is that when j is equal to k, you have this non-zero value for the integral. So let's conclude our lecture for today with the main idea on how this leads to Fourier Bessel series. So in the process of solving a boundary value problem, you will need at some point to write your function on the interval 0c in terms of some series of Bessel functions. Okay, this will be essentially the last part of the problem, right? When you have to match a function with a series representation. And again, it's very important to establish at that point where these alphas come from. Okay, so in the Dirichlet type of condition, if you have this condition, then these alphas are simply the roots of the equation j naught of alpha c equals 0. So for that boundary condition, we showed that these functions are orthogonal with weight function x, meaning that this integral has these values. For different boundary conditions, we will have the same orthogonality principle, but the value of this integral here when j is equal to k will be different. Still non-zero, but different value. So how do you find this representation? So how do you find this aj? Just like in the sine functions, you're going to multiply, you're going to fix a j, multiply the entire equality by j naught of alpha jx. So on the left side, you're going to have the integral from 0 to c f of x j naught of alpha jx dx. On the right-hand side, all those integrals will be 0, except the one in the middle that has the index identical to j, right? So when these two pair out, by the way, sorry, you multiply not by j naught, you multiply by x times j naught, because remember, you need the weight function x. So you multiply both sides by x times j naught of alpha jx. So the non-zero integral will be from 0 to c of x j naught of alpha jx j naught of alpha jx dx. And again, all the other integrals are 0. And this gives you the way to find the Fourier coefficient, the Fourier Bessel coefficient. So let's do one more step here. Non-zero integral we just showed before is c squared j1 of c alpha j divided by 2. So the formula for aj will be, because you divide by this coefficient, will be 2 over c squared j1 of c alpha j, the integral from 0 to c x f of x j naught of alpha jx dx. So I know that it might be quite a lot to take in at this point. To make it easier, again, try to make the analogy with the Fourier series in terms of sine and cosine. And I hope everything comes together in a logical manner, at least when you put everything together, right? So basically, when it boils down to actually solve the boundary value problem, when you end up with matching the series format of the solution with the initial condition, depending on your boundary conditions, those coefficients will be given by these types of formulas. You already have this in the formula sheet if you look at the handout on Bessel functions. So for Dirichlet type conditions, this is the formula for the coefficient. So basically, in practice, either you use a computation tool like a computer, or you can do it by hand if the function is easy enough. So it boils down to solving this integral. In practice, we really are going to solve this integral for examples in which f of x is a power of x, because we have that recursion formula. In general, if you have a more complicated function, you leave the answer in the integral form and maybe have maple or something similar to deal with this. So that's it for today. We're going to obviously go through examples on how to solve. So in the next lecture, we finally get ready to solve boundary value problems from top to finish involving the Bessel function. And then we're going to discuss other boundary conditions. We're not going to go through the same proofs all over again. We're going to have basically two more types of boundary conditions, one in which you have the insulation on the outer edge, so that means the derivative at rho is equal to 0, and some other boundary condition which comes from the Newton's law of cooling, like we know, so the Newton's law of cooling or heating on the surface. That's it for today.